Should be recording. Let me share my screen. All right, hopefully you can see my screen now.
Yes.
Right, so you know that for isomerism, you have just like, all right, if they're the same compound, then they're the same compound.
Uh-huh.
I don't know why it's doing that. Constitutional isomers.
That's it's like the same formula, but I think different connectivity.
And then so conformational isomers. Or stereoisomers. They have same molecular formula, connectivity, different spatial arrangement. I don't know what's happening. And this expands further into diastereomers and enantiomers. And that's what he'll be asking on the test. When he gives you the test, you're gonna have, all right, what's the relationship between these? And you have choices that are the same. He said that he wouldn't give you like different molecules, so that wouldn't be a choice. So they'd be the same constitutional isomers, diastereomers, or enantiomers. And if you've seen the past tests, if you look at the test 2 segment materials, there should be pages that give you practice on that. And the main thing is differentiating diastereomers versus enantiomers. And then I guess the same as well. And the main deal is looking at the patterns. So if we had, for example, three chiral centers, and they were R, R, S. All right, because remember, Fisher projections are relative conformations. So you see how this one's always comparing it to A.
Yeah.
So pretend that was A. If we look at other molecules, so if our main one is R, R, S, I always like writing it out. If we had a compound that was like S, S, R, if there's a complete reversal, that'd be an enantiomer.
Because that would be a mirror image. Okay.
And if it was R, S, S, there's only one difference. So that'd be diastereomer.
Okay. Okay, so we should basically write out the configuration for everything. Okay.
Yeah, that's what I would do. And if I were to, let's go ahead and just work this out. For this one, all right. Nope. This is wedged. This is wedged. This is dotted. I would number them. This is 1. That's obviously 4. This carbon's connected to an O, so this would be 2, and this top one would be 3. And if I were to look at that, that would be S. And going back around, I'm just gonna highlight that S. This is 1. This carbon right here is 2 because that's a carbon connected to a Br. This would be 3, and this would obviously be 4. Wedge. So we would have a S, I think. Gavin, if you're here, was this S? Is this what you got?
Yeah, it was SS.
SS, okay, I thought so. That's S. So now we look at B, C, and D. This one, I'm just gonna do one example of these. I like drawing the wedges personally. So this is 4, this is 1, obviously. This carbon right here is 2 because that's a carbon connected to a bromine, and this is going to be 3. And if I were to look at that, that would be R. I don't know what It's so thick, but that is R. Yeah. Then for this carbon, this would be 1. This carbon right here would be 2 because it's connected to that oxygen. 3, 4. I'm going to erase these. Make some room. That would be what? S. Yeah, S. So right here we have our S. Now, if this was our relative starting point and we have our S, what kind of isomer is that?
So only one of them changed. So would it be a diastereomers?
Because only one changes. If we had an R, that would be an enantiomer because there's a complete reversal.
Yes. And then so if it was still SS, that would just be identical.
Yeah.
Okay.
And the thing is, when you're looking at it visually, these are some tricks I use when I'm doing the test things. So he might have remembered when he said, all right, when you work these problems, especially for Fisher certification, I don't know why I keep saying certification. That's something you do second semester, but just Fisher structures in general, they have to be in the plane of the paper because that's how they were drawn. You can't flip it in any way, shape, or form. You can't pancake flip it side to side or up or down. However, if you keep it in the plane, you can rotate it. So like A, let's just rotate A again. Let me erase this. Let's rotate A. So the CH would trade places with that C, the CH3 would trade places with that. Thankfully, they're the same thing. So rotating it doesn't really matter. This OH would rotate completely over here, and this BR would rotate 180 degrees over here. BR, OH. Then the H is here, and that H here. So if I erase all these arrows, nope. Do you see how I basically just took A and I rotated it while it's on the page? That's something you can completely do. That's completely acceptable. And what do you know? That's what D is. It matches up. If this was SS, well, I know that this is going to be RR. Nope, SS, my bad.
Same thing.
Yep. I'm just going to cross it out. SS. It's going to be the same thing because again, rotated, it's, yeah. Same thing.
Awesome. Perfect. That was really helpful. Thank you so much.
So that's the key thing. Same thing with not even Fisher structures. If we were to draw out, oh, come on. This is stuff I'll talk about tomorrow as well. But if you have a just normal compound, this is what I was talking about when I was when we were talking about question 1. For the chair conformations, I just like drawing it out like this. Like this is what that axial position would be. You know, they're on different planes. If you had something like this, I'm trying to think. I have a really good example. Trust me. CL. That's supposed to be a hexane, by the way. Let's just do a .PR, right? This is something that they could throw out at you. There we go. That's what I was trying to draw. Would this be, what kind of compounds would these be? And you might be thinking, all right, well, we have a CH3 ClBr, CH3 ClBr, and they're in the same like wedged dash pattern, so they must be the same, but that's incorrect. They're they're enantiomers. Because again, you can't pancake flip anything, but you can rotate it and make sure that they line up. So if I were to rotate it, like let's say I want that CH3 to match up with this CH3 and that Br to line up with there. If we were to rotate it, it would look like this. CH3 Br. However, the Cl would be here if we rotate it. And if you look at these compounds right here, that compound and that compound, they're not the same. Yeah.
Perfect.
So that's something they can provide you. Yeah. So
cool.
The main thing I wanted to point with that is like, again, rotating is your best friend because it keeps things in the same plane and you can use it throughout the thing. Hey, what are you looking for? What's this? All righty. Perfect. Request. Bring this to the pharmacy through those double doors. Yeah.
Will be okay because I'm requesting both the pharmacy and the general.
Yeah.
Okay.
Of course. Sorry about that.
All good. And then, so just another quick question, going back to the top, like with that chair conformation. So if you have, like, if you draw it as a Hayworth and the two methyl groups are in different planes, does that mean you can't draw a line of symmetry or a plane of symmetry? Or can you?
Say that again?
So if you have like two substituents that like are in different planes, can you draw a plane of symmetry through that or no?
It kind of depends on the cycle or whatever chair configuration you have. Because if they're 1,4 from each other, you can draw that plane of symmetry right down the middle. So even if you had, let me share. Nope, not yet. I have the answers up. Oh, there we go. Can you guys see this?
Right now I just see like the Zoom launch meeting screen.
Okay, there we go. How about this one?
Yeah.
Okay. If your chair confirmation was something like this. There would be a plane of symmetry because you can just cut it right down the middle. So again, if you have chair confirmations, just write it out like it was, or like this kind of structure, a Kugel structure, and then you should be well on your way to figure stuff out.
Got it. Awesome. Thank you so much for your help, Patrick.
Yeah. Does that answer your question? I don't know if that was specifically what you were asking.
No, yeah, that makes sense. I think if I draw it out like that, it'll be
Yeah,
good.
just draw it out like this and you can pretty much figure out everything else.
Perfect. Perfect. Thank you.
So I had a real quick question for the third one on number 2. So when you're trying to find the priorities, how does a double bond factor into that?
Double bond, you look at the bond, so it counts as 2 C's. So again, you have a C and a C
Okay.
here,
Yeah, so then
and
that
then you're
would
looking at
be
what it's bonded to. Well, 2 of those bonds are occupied by,
yeah, okay.
yeah, that's it. So
All right, cool.
CCH, this would be HHC. Yeah, that's it.
Yep, okay, thank you.
Hey Patrick, I just had a question on the first one, third box.
Sure, yeah.
So I know the first 2 are achiral, but I don't know about this one. I'm not sure if it's achiral or chiral.
Well, the first step is making sure that you have your Newman projections are in eclipse formations. Is that what you did?
Yeah.
Okay,
Wait. Yeah.
hold on. Let me log in. Oh, come on. Sorry, hold on.
No, you're good.
Oh, come on. I was being a little bit. This is a very old keyboard. Okay. When you bring them into eclipse formations, what does it look like? I'm going to have you work it out for me. So let's work for these 2 groups. What do you have there?
It's the CH3 and the H.
It would be
Or-
CH3, CH3.
CH3, yeah,
Yeah, because if you bring this rotation all the way over there,
right,
this rotation will go all the way over here.
okay,
This is something really handy you can use your what is it, your model kit for.
Yeah.
Right. And then what about for this group over here? Knowing that you rotated
that'd be HH,
HH, and then for this one,
and then CL.
all right. And if they match up, then they're achiral. And from the looks of it, all three match up. So pretty good.
Okay, so all three are achiral, and then I know the fourth one is chiral. So.
Yeah, you're correct.
And for number 2, I just want to go over the if I got it right.
Sure.
Um,
Give me 1 second. Let me stop my share. Let me pause the recording.